How goes it?
It goes.
It goes. What questions do you have?
Are you willing to move the test from Thursday to like Wednesday? Move it back.
How are you?
Or whatever. Take it.
You want to fill your water bottle? I'd leave it open since the door's locked.
Yeah, he doesn't want me coming into class.
No, I don't leave it open. Okay, that makes more sense then.
I've been quiet every time I've come in.
I didn't say you haven't. You've been perfectly fine.
Yeah.
You've been perfectly fine.
So you locked me out.
I didn't do anything. The door was just locked. I didn't lock the door. I have absolutely zero control over whether that door is locked or not.
I'm pretty sure you're just like you're like the door whisperer. You just
You
like
just whisper the door and lock it. That'd be fantastic. Any other questions at all before we get doing some more examples of the stuff we were talking about last time? All right. Well, right at the end of class last time, we talked about the definition of independent events. And in particular, talked about how we can calculate the probability of an independent, the intersection of independent events just as the product of the probabilities of the events themselves. So to that end, let's look at number 3.9 on that packet that I handed out last time. Thank you, Chelsea. Anything else you need, Chelsea?
Give me the air.
All right, so 3.9 says 3.9 says that you've got 3 dice. You're going to toss them independently. Each of the 3 events that you're interested in is the fact that a 6 shows up. And it asks you what is the probability of E1 union E2 union E3. Before we do it with the formulas, which we'll be able to do here in a minute, but before we do this, in words, what is that actually looking for? If each of your events is the probability that a 6 shows up on each individual die, what is the probability of E1 union E2 union E3 in words? The probability of what? Okay. In the context of the problem, using words, what is it?
You get a 6 of 1. Another dice.
Okay. And that's one of the possibilities, right? You could do the 6 on all 3. But since we're using union, does it have to be all 3? At least one. That's the word that I'm looking for. Yeah, at least one of the guys has a 6 on it. That was the word that I was looking for. The union of the E1, union E2, union E3, in the context of this problem, means that at least one 6 is thrown. Now, would it matter, if from a probability standpoint, would it matter if you throw 3 independent dice or 1 die 3 independent times? Would the probability change? Or would it be the same? Be the same, right? So you could. So a problem also could have said, say you throw a die 3 times. What's the probability of getting a 6 at these points? It'd be the same probability, right? So there's a couple of ways to attack this. The first way is just brute force using formulas to attack it. Let's think about our formula that we have for union. And then we'll go back to the at least one idea and see if there's another way to attack it. All right, if we brute force this with formulas, how do we take the probability of a union, just in general? Usually we think about it in 2 sets. How do we do a probability of a union of 2 sets? If I have probability of A union B, you have the probability of A. Okay. Good, minus intersection, right? We agree? Okay. So here we could think of this as, this is one, if I want to think about how we do it for 3, I can think about grouping the first 2 together and think of it as a union of 2 sets, right? And using that formula, we could write that as probability of E1 union E2 plus the probability of E3 minus the probability of the intersection of those 2. Right? Okay. So if we break this up a little bit more, this first one is now the probability of a union of 2 sets. So we can break that into the pieces again like we did before using the same formula. And then I still have that other piece on the end. I'm trying to break this up into as many pieces as we can here. So let's look at that last piece. Notice it's an intersection right now, but we talked about this last time. We've got parentheses here and an intersection on the outside. What can I do with this intersection? This kind of reminds you of algebra. What can I do with this intersection? Distribute it over the union, right? So we can write that last piece. Let me just do this on the side, down here at the bottom. We can write that last piece as the probability of E1 intersect E3 union, union E2 intersect E3, right? We're distributing the intersection over the union. And now I've got a probability of a union again, don't I? So we can do the same thing that we did before with that. We can do this as probability of E1 intersect E3 plus the probability of E2 intersect E3. Add them up, right? And then what do I have to subtract off? The intersection of the two things, right? I didn't say it was pretty. I just said you can do it this way.
Yeah, there's going to be a nicer way.
There's going to be, I think, a nicer way to do this.
Okay.
But there's another reason why I'm doing it this particular way, because this gives you when we're done, we're also going to have a formula for doing the probability of the union of 3 sets if you need it. You don't use it a lot, but it does pop up from time to time. So it was one of the reasons why I wanted to do this. All right, so let's look at this last little bit here. I've got E1 intersect E3 intersect E2 intersect E3. I can probably simplify this a little bit more.
No.
Oh yeah.
No.
Yes. No, I don't need to use De Morgan. I've got the same thing here both times, don't I? Think in words of what this would mean. I needed in E1 and E3 and E2 and E3. What's redundant? The E3 twice, right? So I can just write this as probability of E1 intersect E2 intersect E3. Okay, great.
Up here, when we're talking about the probability of E1 or E2 and E3, and it's down here again, there's a minus sign right in front of that. So when we expand that, we have the...
Yep. That's what I'm going to do here in a second. Yep, you're right. All right, so this part, again, this part right here is E1 intersect E2 intersect E3. And like Grace pointed out, I pulled this piece out here, the piece that I'm underlining. I pulled this piece out, there's a minus sign in the front. Right? So I'm going to need to distribute the minus sign through. When we do that, let me collect things that look similar. So we've got probability of E1, probability of E2, probability of E3 are all positive, right? What about the intersection of an individual two, the probability of just the two intersections? What are all those signs going to be? They're all going to be negative, right? Right? So this will be minus the probability of E1 intersect E2 minus the probability of E1 intersect E3 minus the probability of E2 intersect E3. What's the sign of this last piece going to be? It's going to be positive. So you'll have plus probability of E1 intersect E2 intersect E3. We did it. Okay? So again, this gives you a formula with how you could do this by how to do the probability of a union of three things. If you think about it just intuitively, you see why this works. I want to basically think of a counting argument. I need to count everything that's in the union. So I need to count everything in E1, everything in E2, everything in E3. Now let's think about double counting. What gets double counted? The things that are in the intersections, right? So we're going to subtract all of those off, correct? Well, let's think about here. I've counted, what have I counted here? I've counted everything in all three of them 3 times, right? And I've subtracted them all back off again a couple of times. So I have to add it back in there because I've subtracted off too many times. You think about it intuitively. You don't have to. So if you do, you do it that way. All right. I know it was ugly. I just wanted to show you where the formula comes from because it does pop up from time to time. You'll see it in your textbook. You'll see it other places. You see it in set theory. You'll see it counting up the number of things in a union of 3 things. How does it apply to this problem? All right, so let's think about it. What is each of these events in this problem? The events are what? Rolling a die and getting a 6, right? We agree? Now, one of the things that we're talking about is that they are independent, right? So when you do the probability of the intersection, how do we do the probability of the intersection for independent events? What do we do with the probabilities? When we do the probability of A intersect B, what did we say last time that was equal to? Yeah, probability of A times probability of B, right? So when you get to this part, we just need to multiply the 2 probabilities, right? Same here, same here. What do you think we'll do in this part? Multiply all 3. So when we do that, if we do that in this fashion, for this particular problem, the probability of E1 intersect E2 intersect E3 will be 1/6 plus a 6 plus a 6. That's the probability of rolling a 6 on each of the individual die, right? Is? Okay. Minus, we want first die and second die both having a 6. That would be 1/6 times 1/6, right?
Sorry, did you mean to write union?
I did mean to write union. Thank you. Don't apologize for my error. Thank you for telling me. And then the same thing, what's this? This intersection is a 6 on the first and a 6 on the third, right? So that one will also be a 6 times a 6th. And the last one, or the next to last one, the E2 intersect E3 will also be a 6 times a 6th. What will the last one be? Yeah, well, 6 times a 6 times a 6. Right? This was I know, it's not I didn't say it was the most pleasant way to do it. I led off with that. All right. And then if you put all these pieces together, you get a nice little fraction, right? This is, what do you get? Anybody do this on their calculator? So you can't help a guy out? Seriously?
91 over 260.
Good. Thank you.
Somebody's license.
Thank you. I can do it. I just feel like doing it in my head.
We can all do it.
You can all do it. I don't feel like doing it. All right. So again, just to go through intuitively what's going on, adding up each of the probabilities, so counting the number of ways that each individual die can come up with 6. Subtracting off double counts, you subtract off the double counts you've added up, or you subtract off triple counts, ends up being 1 too many times. So you have to add it back. All right. That's using the formula going straight forward at it, just trying to use the formula and the properties of being independent. That is an ugly way to do it. I think we can agree that was not the prettiest way to do it, correct? If for no other reason, then I have to write a 6 plus a 6 plus a 6 minus, and then I'll get 1 6 flying everywhere, right? Let's think about a different way we could do it. You told me to start off this problem that in words, this said the probability of rolling at least 1 6, right? So that means you got 1 6 or 2 6s or 3 6s. And as we just saw with this formula, that's complicated to count, right? Can we think about the complement instead? Sometimes the complement helps. What is the complement of at least 1? None. Oh, wait. Can we calculate the probability that you get no 6s? That would be you did not get a 6 on the first, and you did not get a 6 on the second, and you did not get a 6 on the third. There's no unions in there at all, right? If you get no 6s, that's no 6 on the first, and no 6 on the second, and no 6 on the third. That's a lot easier to compute, isn't it? Much easier to compute. So if I want the complement, the probability of the complement of this is going to be the probability of the intersection of the complements. That's De Morgan's law. So this will be the probability of the complement of the first times the probability of the complement of the second, complement of the third. Notice no sum formula, no nasty long formula, right? This probability of an intersection, if they're independent, so I can make it just, they're mutually independent, so I can just make it the product of the 3. What's the probability of not rolling a 6 on any individual roll? 5 6, right? So this would be 5 6 cubed, or 125 over 216. Because I haven't finished the problem. Because did I compute the probability of what I wanted? No, I computed the probability of the complement, right? The opposite of what I wanted. So how do I get the probability that I do want? Subtract it from 1. Yeah, that's exactly right. So the probability of E1 union E2 union E3 will be 1 minus this probability. And now I get the same answer. Which way did you prefer?
Oh, I don't know.
Huh?
I go back to first.
Hey, you want to go back to the vote? That's fine. You can do it the very first way. We did, didn't we? I know.
What's it though?
I like sarcasm.
Do you really?
I really do. Shockingly enough, if you hadn't been able to figure that. All right, so when you do these problems, I think, especially if you've got something that can be interpreted as at least 1 or even at least 2, usually those are a little bit better computed by doing the complement. It's like both these. Is okay? All right. Let's see if we can do another one that involves independence. Let's do the very next one, the 3.10. Part of these problems that are in this particular packet are preparing you for different types of distributions that are going to happen later on this semester. Different types of probability distributions, and we'll get to those in the next chapter. All right, so this one says you've got 35 diamonds. It says gems. 10 are real diamonds, 25 are fake. Well, then that's not all gems, but that's okay. Some of them are just rocks.
Fake gems.
You're going to take them randomly out of the box one at a time without replacement. It says, what is the probability that exactly 2 fakes are selected before the second real diamond is selected? So let's think about it in terms of what are your possibilities, and let's think about what has to happen. We want exactly 2 fakes before the second diamond is selected. Okay? So I've got 2 fakes and 2 diamonds. Right? Is it exactly 2 fakes before the second diamond is selected? Right? Yes.
So does that mean that you have 1 diamond, 2 fakes, and then the second diamond?
That's one of the possibilities, right? You could do 1 diamond, 2 fakes, and then the second diamond comes out. Or I could do fake, fake, diamond, diamond like I wrote here, correct? The 2 things that we know for certain are what? There's exactly 2 fakes. Then what has to come out on the last pull? A real one, right? You agree? So for example, this doesn't make sense. Oops. That doesn't make sense, right? That one doesn't work because I've pulled out 2 diamonds, but I haven't pulled out any fakes before, right? So that arrangement doesn't work, correct? Or, good Lord, I can't write anything. That arrangement wouldn't work either, right? Because that would be exactly 1 fake before the first diamond's selected, right? Okay. So this one is fixed. Basically, what do we have? We have to have 4 draws, correct? We're not going to have any choice. You're going to have 4 draws, but that last one has to be a diamond, right? So let's think about just pulling that diamond on the last pull. Well, if I've already pulled 3 gems out, one of which has to be a diamond, what does this probability have to be? Okay, 9. I agree, there's 9 diamonds. How many things are left in the bag? Or box, or whatever? 32, right? If we're saying that the last one has to be a diamond, and it has to be the second diamond, right? We've already pulled out 1 diamond. We've already pulled out 2 fakes, right? Then there's 32 gems left, and there's 9 diamonds that are left. So that one has to be 9 out of 32, right? You agree? Okay. So let's just think about this first 3. Does the order of those first 3 matter? No, yeses and no's. But what's the important part of the first 3? There's 1 diamond and 2 fakes. Does it matter which order we pull those out in? No. As long as there's exactly 2 fakes and exactly 1 diamond, that order doesn't matter, correct? Okay? So out of that selection of 3, how many total possibilities of selections do you have? 35, choose 3, right? And you told me that 2 of them have to be fake, 1 has to be a diamond, right? We agree? Okay. How many figs do we have to choose from? 25. And how many diamonds? 10. Now, that doesn't necessarily look like one of the answers, does it? Not yet. You could go through and compute and see which ones it has to be. Hopefully it's pretty clear that it's not D or E, because you're not squaring any of those things. Yes. Is it B? Did you already figure it out, I take it? 675 over 5236?
Too quick.
Is that what others got?
I didn't do it.
I just give me 1 second.
We are not as quick.
I just did it.
Come on, Grace.
Dr. Joe, I can't right now.
Here's my B to it. Oh, please. That just proved us some shit.
How do I turn this into a fraction?
You were so
That's what I got, but it didn't let me turn it into a fraction. It just gave me a spit decimal back out of it.
What is it? What did you get? What did you get?
1, 2. Yes.
Okay. 129? Okay,
Didn't
cool.
give me a
Which is B? I just wanted verification we got the right thing. All right, so let's think about one of the reasons why choice D is on there is because of one word. Change one word in the problem and you'll get D instead of C. Okay, and that one word is to change the word without to with. Okay. Let's see why that would be the case. If I changed without to with replacement, notice that you still have the same setup. I would still need diamond on that 4th draw. I would have 2 figs and 1 diamond. There's 3 choose 2 ways to rearrange this. Because I have 2 spots, I have 3 figs and 2 places where to put the figs. The probability of drawing a fig is 25 out of 35, right? You'd be doing that twice. The probability of drawing a diamond is 10 out of 35, you'd be doing that twice. So if you change the word without to with, you get answer D instead of answer C.
B. Sorry.
B, I'm sorry. Say it again?
Where's the 3 choose 2?
The 3 choose 2 comes from rearranging this FFD around. So if the 3 choose 2 is, basically, I've got 3 slots in which to put 2 Fs. So I just pick 2 of the 3 slots to put the F in, and the D has to go in the remaining one. So you have 3 choose 2 different ways to rearrange those letters. So yeah, instead of B, sorry, I said C. But if you change the word without to with, you get D, and that's why the answer D is on there. It's a good distractor if you don't read it closely. With the word without, are the events of pulling out these gems, is that independent? If I use the without replacement, is the events pulling out one at a time here, is that going to be independent or dependent? They're dependent, right? Because I'm changing the sample size each time, right? But if I throw them back in and do it with replacement, are those draws independent? Yes. All right. Let's do. You want to do the next one? Okay. Looks confusing. Okay. Oops. This one says, do R, S, and T be independent, equally likely events with common probability 1/3? And it wants the probability of R union S union T. So I think, just like the first problem that we did, I think we can think about it in 2 ways. using the formula, you could break it up, right? Just like we did, instead of having 1/6, you would have 1/3. Right? It would look exactly the same, you would just have 1/6 instead of 1/3. But probably the easier way to think about it is doing what? Complements, right? If we do the probability of the complement, what does the complement change the union into? Intersection, right? If I want the probability of R union S union T complement, that's going to be the probability of R complement intersect S complement intersect T complement. Since R, S, and T are independent, R complement, S complement, T complement should be independent, right? If you need proof of that, that's actually in the book. I believe it's in the book. Yep, it's theorem 1.5-1 on page 40. So if R and S are independent, R complement and S complement are also independent. It's not a difficult thing to prove, actually. It just involves using the formula. So this will be probability of R complement times the probability of S complement, probability of T complement. And what are each of those probabilities? 2/3, because we're doing the complements of the events, right? Is that the answer we want? No. What do we need to do with that? Subtract it from 1. Good.
Whole circle.
The whole circle?
The whole pie.
We did do it. It was very exciting.
He's always.
Let's do another one kind of like this one. This one was just like the first problem we did. Let's do another one like this one. Let's look at 3.15. A, B, and C are events with A and B independent, B and C mutually exclusive. They give you the probabilities of A and B and C individually, and they want the probability of A intersect B complement union C.
Is this one going to be easier to think of as A naught complement or A naught union B naught, or is it, or should we keep it like that?
I like that. That looks good to me. Why not? It's fine with me. We can do it that way. Which part? So, from here to here?
Yeah.
Okay, so when we do the complement of the intersection, it flips the intersection to a union, and then we do the complements of each individual piece.
How many is distributed to complement?
If you distribute the complement, it just flips the sign in the middle. If we think about if you want to think about the picture itself, this is A intersect B here in the middle, right? So the complement of that would be everything outside of that middle piece. And notice that's everything outside of A, union with everything outside of B. The piece that you miss is here, if I union those two pieces together. Hear a lot of hmms. Ooh. What thoughts do you have? Yeah.
What's the difference between
What is the difference between independent and mutually exclusive? The intersection is empty, right? So we know that B intersects C is the empty set, right? Whereas independent would say that the probability of A intersect B is probability of A times the probability of B, right? What's that? Oh, okay, think about it this way. How would that be, what would have to happen if those were also mutually exclusive? What would that product have to equal? If mutually exclusive means B intersects C is the empty set, if A and B were also mutually exclusive, what would this product have to equal? If they're mutually exclusive, their intersection is empty. What's the probability of the empty set? Zero. So would that product have to be zero? Yes. So what does that tell you about one of the factors? It would have to be zero, right? Which would tell you that one of the events is impossible. So the only way you can be independent and mutually exclusive at the same time is if one of them is empty. One of them is an impossible event. I think they both could be. But the only way that you can get mutually exclusive and independent at the same time is if one of them is empty. At least one of them is empty. One of them is impossible. That's a good question. A lot of people have issues with independence versus mutually exclusive. They're almost completely separate ideas. There's not a lot of connection between the two. If you're mutually exclusive, you're most likely not independent.
So like the independent is like the coin toss, having another one. Like
Yeah.
that's not independent.
Right.
But when you interpret mutually exclusive as they have nothing to do with
Well, mutually exclusive, in that case, though, mutually exclusive, it means they can't happen at the same time. So I flip a coin, I could certainly have heads on the first flip and tails or heads on the second flip. So those would not be mutually exclusive events. I could have heads on the first or heads on the second or heads on the first, tails on the second. All those. Those are not mutually exclusive because they can definitely happen at the same time. This would say whatever happens on the first coin can't happen on the second coin. But that doesn't make, if we're flipping coins, that doesn't make any sense if they're independent. You can certainly have that happen one after the other.
So we use that to say that the probability of A complement intersection C is also zero. You said that it can't happen.
A complement? Which one? I'm sorry?
Like whenever you go through, so for A to happen and for C to happen, like the intersection of A and C, would that also be the empty set then?
I don't know about A and C necessarily. But I do know something about B and C, or B complement and C.
Is B complement intersections, or B complement union C just equal to B complement?
Yeah, it has to be. Yeah, it does. It has to be.
Okay. So then,
Yeah, so think about it this way. So think about the picture, right? If I'm just worried about B and C, if B and C are mutually exclusive, then that's what we have, right? We have non-intersecting circles. So if I do the complement of B, where does C have to live? Inside the complement, right? So when I take B complement and union C, it has to be entirely inside of B complement, which tells me that this is just what? Probability of A complement union B complement without the C. I don't need the C in there. That's a very good observation. That's exactly right. The C is just completely absorbed inside the B complement. So in fact, you might have been able to see that here. Certainly the complement of A intersect B is going to contain the complement of B, which has to contain C. So this goes all the way back to, probability of A intersect B complement. Those two things are equal. So this will be 1 minus the probability of A intersect B, using our properties for complements. Okay, so first, let's just go back and see what we did. We used mutually exclusive for what? From this, we got this piece down here, right? From the fact that B intersect C is empty, so it tells me that C has to be entirely contained in the complement. Right? So mutually exclusive got me here. Which allowed me to rewrite the probability that we're looking for as just the probability of A intersect B complement. Notice now the probability of C is irrelevant. They gave us information that we're not even going to need to use. Okay? Then we can just use the probability of the complement to get to this next part. How do we use independence? How do I calculate this piece now? That's probability of A times probability of B. There's where independence comes in. Probability of A is a fourth, probability of B is a sixth. So we get 23 out of 24?
Yep.
All right. Let's look at one more. Let's look at, this is 4.2 on that new packet that I handed out. This is going to lead us into new stuff, which talks about Bayes' theorem. The actual name of the theorem is irrelevant for calculating the types of probabilities that we're going to do. The idea is the crux of the idea is exactly what we're going to do in this particular problem. So it says an urn contains four dice. Two of them are normal dice. One of them has only 2s, 4s, and 6s, and one of them has all 6s. You're going to pull out one die and roll it twice. And you're going to see what the probability is of getting a 6 both times. All right, so the crux of what we're going to be doing in the new stuff in Bayes' theorem, which is section 1.6 of your text. The crux of what goes on in Bayes' theorem is that I need to split up a bigger probability into smaller chunks. Okay? So the bigger probability here is the probability that you roll a 6. Well, the probability that you roll a 6 twice, but in particular, it's the probability that you're rolling a 6, right? Well, that probability that you roll a 6 depends on which die you select, right? Do I select one of the normal die? One of the normal dice? Do I select the even numbered die? Do I select the die with only 6s, right? That's splitting up my bigger probability into 3 distinct categories, right? You agree? So the probability of rolling 6 twice, we're going to split it up into 3 distinct pieces. Now, since these are distinct pieces, and what I mean by distinct, I'm saying the wrong word. What I really mean are disjoint pieces, right? You're pulling out one die, correct? Okay? So I can't pull out the normal die and the one that has all even numbers on it. If I have disjoint cases, what are you going to do with the 3 probabilities here in this case? Add them, right? Are you agree? Okay. So the fact that we've broken up the big case into 3 smaller cases, and we know that they're disjoint cases, so all we have to do is add them to get our probabilities, right? All right, so let's think about the 3 cases of normal die, even die, and the all 6 die. All right. If I know I have an even or a normal die, what's the probability of rolling a 6? 1/6, right? If I have an even die, what's the probability of rolling 1/6 in that case, or a 6 in that case? 1/3, right? Because 2 out of the 6 possibilities are 6s. If I pull an all 6 die, what's the probability of rolling a 6? 1. Now remember, we're rolling a 6 twice, correct? All I've written down are the probabilities of rolling a 6 one time, correct? To get the probability of rolling a 6 twice, what do I need to do with each of those numbers? Square them. Yeah, I need to multiply them by themselves. Good. So far, so good? No, I'm not done, but so far, so good? Okay. But notice that I started each of those with, if I know which die, those are the probabilities, correct? Okay. So I don't know those particular, if I have those die, so I have to calculate those probabilities, correct? What's the probability that you draw out a normal die?
1/3.
It's 2/4, right? It's 2 out of 4. 2 out of the 4 are normal, right? Because you're only pulling the one die out, right? But 2 of them are normal.
What was your question?
I said, what's the probability that you pulled out the normal die? To be able to get into the normal die case and roll the 6 twice, I have to pull out a normal die. There's 2 of them, yep. How about the even die? What's the probability that you drew out the even die? 1/4. And then what's the probability to draw the all 6 die? 1/4. Now let's think about why I'm putting the multiplication symbols in there. To get into this case, I had to draw the normal die and roll 6 twice. Right?
Where's your extra 6?
That's a dot.
Really? That's a dot?
That's a dot.
That's a dot.
Okay, we're going to criticize my dots. Okay.
That's a dot. You had a 6 and you know it.
How about that? Is that better?
Still a dot.
It's still a dot.
I don't know, some of it's the basketball. It looks like a meatball.
That's a 6.
No, it's an upside down comma.
No. Yes.
Yeah, it's an upside down comma.
It's a 6 filled in.
All right. Anyway, this comes from drawing the die and rolling 2 6s, right? But that's not the only possibility. We could have also drawn the even die and rolled 2 6s. Or we drew the all 6 die and rolled 2 6s. So we broke up our big probability into smaller disjoint pieces and calculated them essentially with conditional probability, right? The probability of rolling a 6 twice is you pulled the normal die and rolled the 6 twice. or you pulled an even die and you rolled the 6 twice, or you pulled all 6 die and rolled the 6 twice. Some books call this the law of total probability. We'll write more of this down next time. But this entire concept of being able to do the stuff that they refer to as Bayes' theorem in section 6 is literally just being able to break the big probability into smaller pieces. Okay? All right, we'll do that next time. Have a good one. I'll give you more homework to do next time, too. Yay!
So much fun.
I still like sarcasm.
Yes. You failed.